Right. So good morning to all of you here. How was your homework from yesterday? I think there were some questions that somebody wanted to have answered. So very quickly, we'll answer a quick question here. You had a question on one of the moment of inertia problems here. So I will grab it out for you. Okay, your question on was number 59 in the homework. Okay. Okay. So in 59 we have a little bit of a figure. We have two cylinders, something like this. And we have something, this mass of 4.0 kilograms. And then we have the second one on an outer cylinder, something like this, 2.0 kilograms, 2.5. And they want us to find the angular acceleration of the two. Mm-hmm. And we're assuming it on a frictionless scale. So to do this problem, I'm going to erase my pretty picture. Well, I'm going to erase my pretty picture and we'll come back to it later. Okay. And so what is given to us, we're told that the smaller cylinder has diameter of 10 centimeters. So quickly doing that in our head, okay, the diameter, which is equal to twice the radius, which is equal to 10 centimeters. Thusly, as you know, there's 100 centimeters in a meter. So really, very quickly, 1, 2, moving it back, so it's 0.1 of a meter. Okay, we're also told mass of it, big M, is 5.0 kilogram. Now we're nextly told, okay, we're nextly told that the second one has diameter of 20 kilograms. 20.2 meters, 0.2 meter, and it has big mass 2 of 20 kilograms. We're also told that mass, little mass, oops, and we're also told little mass of the first one is equal to 2.5 kilograms, 4.0 kilograms, and we want to find alpha, or the angular acceleration. Okay. Okay. We have two cylinders, so let's draw them separately. So this is for our solution. Um, well, first we'll draw them together. I'll have the picture. Will be M2, and this will be M1. Okay. So we have two pictures to draw, or actually four, for visualization purposes here. Okay, this will be, oops, where did my hand go here? R1, R2, D1, D2. Okay. Okay. All right. So if we draw out the second one, or the larger cylinder here with the diameter here, like this. We have tension coming this way up. Why? Because mass 1, the one that's on the outside cylinder is the smaller mass. So we know already that it's going to go like this. So we'll direct the angular acceleration this way. And this is the directed attention of the rope. T1, we'll call that. Okay. Or yeah, we'll call it T1. Okay. And this is our diameter D. Okay. The smaller cylinder, which will be over here, that will be D2. And this will be T2 going down like this. And angular acceleration, again, directed that way. Okay. And we'll take care of that later. And then we need a free body diagram, of course. And this is going, so the free body diagram here, for the larger cylinder, T1 is bigger than M1G. And for right here, M2G is bigger than T2. Okay. Acceleration, acceleration. Everybody follow so far. What's going on here? We have we have basically the big cylinder, which has the smaller mass. It's going to be led down by M2. It's going to twist and turn until it gets all the way up there. Okay. And so we need to find the angular acceleration of this system. Okay. So we're going to set this up two ways. Okay. First, dealing with sum of forces here. First, we'll deal with the sum of forces, then we'll deal with torque. Okay. So sum of forces in the y direction will be T1 minus M1G. Why? Again, because the tension is pulling the weight. So it's important that you're able to see that. the tension in this case overcomes its weight, okay, in the fact that it's going to be going this way. Now it's going to get stuck at the top, but whatever, no big deal. Okay. Same situation here for this. In the second part will be m2g minus t2. Okay. Everybody with me so far? Good, is that? So we're able to see kind of the setup of the problem here? Okay. Now, from here, what do we do? Right? We will use Newton's law to help us to set up the equation. Now, because they're moving as a system, moving together, the angular acceleration for both cylinders should be exactly the same. Okay. Okay, even though there's different tensions in the rope, they should be, the angular acceleration for the system should be exactly the same. So these will undergo exactly the same acceleration. We do not need to find out at all what that acceleration is, okay? Because we're looking for the angular acceleration. So using Newton's law here, okay, we're going to be able to solve for tension 1 and tension 2. From this, we can imply this. Times A. Okay. Everybody following so far? Okay, good. So can I erase it? So far, everybody following the setup. Okay, I'm going through, I know I'm taking a little bit more time in explaining the problem this way. You're seeing the understanding of physics that's going on here. Okay. I'm going to go ahead and erase this now. So we have T1 minus M1G equals M1A. And then from here, M2G minus T2 equals M2A. From here, T1 equals M1A plus M1G. T2 equals M2G minus M2A. Alright. Now we have to set up the sum of torques in this situation. Okay. This is T1. And this is T2. D2, D1. Okay. Recall, okay, I've defined angular acceleration to be going this way. I've defined angular acceleration to be going that way. So, in that sense, normally when we say it's clockwise, we're implying a negative angular acceleration. Okay? But for the sake of simplicity, we'll make it positive. Why can I get away with it? Because they're both going in the same direction. So Okay. So now we have R times tension 1 plus R1, R2 times tension 2. Okay. So far, everybody with me? And this will actually end up being the sum of the moments of inertia here. Okay. R in this problem is not given, true? We're given the diameter. So we know that the radius is, of course, the diameter divided by 2. So it's d1 divided by 2 times t1 plus d2 divided by 2 times t2. And that's our sum of torque. Okay. T1 and T2 we know from here. We know T1 and T2 from this situation here, so we can get away with it and plug it in. Okay. So this is equal d1 over 2 times tension 1, which is m1a plus m1g plus d2 over 2 m2g minus m2a equals our sum of torque. Okay. Now, from here, I know from here what I want to do is to get all accelerations on one side. I want accelerations together, and I want gravities together. So going through all that, we should end up with, okay, because we'll come back. We'll deal with this sum of torque in a bit here. So let's organize it. Okay, can I go ahead and clear it? Let's organize the problem here. So this ends up being, oops. Hold on here, we're having a little bit of an issue. There we go. Okay. So now, the sum of torque equals d1 over 2 m1a minus d2 over 2 m2a plus d1 over 2 m1g plus d2 over 2 m2g, like that. Okay. Now that we know that, we can work with the sum of torque. So we know that the angular acceleration is directly proportional to the sum of torque over the total moment of inertia, I total. Okay? Right? Just like with Newton's law, with the sum of the total mass, it's the sum of the total moment of inertia, which is probably the trick that you probably had to deal with in this problem. And we're going to be able to recall very easily every single one of those moments of inertia, which you all have memorized, of course, because I'm sure that all of you have completely and totally memorized those moments of inertia that are in the back of the book, or in the table right there. And if you didn't, don't feel bad, because nobody asked you to memorize those. And since it's a solid cylinder, it's 1/2 mr². So But we're going to do some manipulation in this equation. From here, I can state that the sum of torques is equal to the total moment of inertia times alpha, the angular acceleration. Okay. Okay. So from here, I know what this will be. The total moment of inertia will be 1/2 m1 d1 over 2 squared, because r is not given, plus 1/2 m2 d2 over 2 squared, once again because r is not given, alpha. And that's this situation here, like that. Okay, equals the total sum of torque. Now, acceleration is equal to r times alpha. This linear acceleration is r times alpha, the angular acceleration. So now we have a total way to be able to combine it together. So let's do that. Okay. So looking at this becomes d1 over 2 m1 times, and which is, by the way, r1, which ends up being what? Which ends up being d over 2, right? So d1 over 2, because r is once again not given, d1 over 2 times alpha, and we'll work that later, minus d1 over 2 m2 d2 over 2 times alpha plus d1 over 2 m1g plus d2 over 2 m2g equals the mess that's over here. Okay. Now we have alphas we want on the same side here. Okay. After doing the painful algebra to simplify the bottom here, so that becomes d1 squared over 4 m1 alpha minus d2 squared over 4 m2 alpha plus d1 over 2 m1g plus d2 over 2 m2g. Everybody with me? Okay. Nothing too painfully on the algebra part. Now we're going to take the alphas and put them on one side of the equation. So that all equals this. So after all this, can I erase it? Yes, no? Well, I'm going to erase it. Okay. So after all this mess, we have to do like this. Okay. We end up with d1 over 2 m1g plus d2 over 2 m2g equals 1/2 m1 d1 over 2 squared plus 1/2 m2 d2 over 2 squared times alpha plus d2 squared over 4 little m2 alpha minus d1 over 4 squared M1 alpha. Whew. Ugly, right? Okay. So alpha factors out from here. From here we can factor out an alpha. And now it's where it gets to be pretty. And we could actually factor out 2, 4, 8. We can actually factor out a 4 from here. But we can factor out 1/4 from here. We have this fourth, this fourth. This is 4 times 4 times 2, 8, 1 to 8. So we end up with, we can factor out 1/4 from this equation. We'll do that. Okay. To factor out 1/4, that becomes 1/2 big M1 d1 squared plus 1/2 d2 squared times M2 plus M2 d2 squared minus M1 d1 squared. Like that. d2 over m2g. Divide, multiply. So multiply by 4. Multiply by 4, divide by this whole mess. So we end up with twice equals alpha times that whole mess over there. All right. And by that whole mess, I'm referring to what's next to it. Because I'm too lazy and don't want to write it for you. All right. And so the angular acceleration, after all that painful work, is factor out to g all over you think there's anything we can factor out of here? Of course there isn't. So we'll just leave it as such. 1/2 m1 d1 squared plus 1/2 m2 d2 squared. And if I really wanted, if I wanted to really do a bunch of algebra, I could at this point, but there's no need to, so we're not going to. Plus m2 d2 squared minus m1 d1 squared. This is the angular acceleration expression you should have. Okay. From that, you should be able to plug in your numbers and get the answer, which in the back of the book, because I give you all the odds on purpose so that I don't have to write the solutions for them. No. Alright. So the answer to number 59 in the back is 3.5 radians per second squared, which you will get, I promise you, alpha 3.5 radians per second squared after you plug it in. But that's the setup algebraically, because that's what you guys were telling me you guys are having trouble with. So I'll have that set up for you. Now I do have something I do need to get through today, so let's get through it. Okay. Any other questions? No? Хорошо. Good enough. Let's go. So, recall, we have been talking a little bit about this moment of inertia concept, and this moment of inertia, right, is the measurement of the resistance to rotation. And I mentioned it in last class that we could quickly find the moment of inertia depending on its axis, what we call the parallel axis theorem, by stating by adding just a factor of h squared to it. And I didn't go about proving this. This was the parallel axis theorem. And I didn't go about really proving it, I just kind of gave it to you in class. So, and that height is with respect to the point of center of mass. Right, this h is the distance. Okay, I didn't really go about proving it for you. I mean, this isn't math class at all, this is physics class, so I don't really necessarily have to prove it, but I will prove it because I'm a nice teacher for you. So, we'll do it like this. Okay. So this is the proof of the parallel axis theorem. Please write it down. All right, so first we're going to need a visual. Okay. We'll start with the point center of mass. We'll start with the center of mass at this point. Okay. Here, we'll create an arbitrary point. We'll call it A. And then we'll call this point dm. Looks kind of familiar. Looks like a triangle, doesn't it? We'll call that angle theta right here. This will be r. This will be r with respect to the center of mass. And this will be some distance, arbitrary distance, we'll call it h. Okay. How many of you are familiar with the law of cosines? Right, you should recognize the law of cosines for that. Okay, that's what we're using here. Okay, these are technically vectors. This here is a vector. This here is also a vector. This here is also a vector. So, since we're going to be using the law of cosines to show this, okay, I don't need to prove law of cosines, but that's in your math class. This is physics class. We don't have to prove it. So, by the use of law of cosines, we'll use my favorite color, which is blue. Okay. It's actually a fairly simple proof, which takes no time. So, using law of cosines, this is the angle in between h and r, and we have the side that's opposite of it. So we have r squared equals h squared plus r cm squared minus twice magnitude of h times magnitude of r times cosine of angle theta times the cosine of angle theta, which is the angle between them. This represents the dot product of those 2 points. So I will write this without the vectors. So r squared is equal to h squared plus r center of mass squared minus 2 h dot r. Easy enough, correct? Nothing too painful to this point. This ugliness goes inside of our integral. Okay? inside of our sum. So we know that moment of inertia is the integral of r squared dm, or the sum of all the r squareds added together, okay, with respect to its center of mass. Okay, I can do that by plugging this in. So I can do that by plugging this mass into the equation. Okay. So it becomes h squared plus rcm squared minus 2h dot r dm. So that's the algebra piece of the puzzle. And then we integrate it. Now, recall that the integral sign can be distributed this way, that way. This gets distributed that way, and that way. All three. So this ends up being the integral, or the sum, of h squared dm plus the integral of rcm squared dm minus twice the integral of h dot r dm. Everybody with me? Okay. No need to do any fancy substitutions. We're just straight integrating with respect to center of mass. Integrating with respect to mass. So that becomes mr squared, or mh squared, sorry, plus mrcm squared minus absolutely nothing. Why is that? Because this particular integral, if you can look very closely and attentively, that it's being integrated, or integrated with respect to the center of, it's integrated with respect to the center of mass, which you would think would just be dm times h times r. Well, that actually ends up being 0 because you're about the origin at either point here. Okay? So if we're considering with respect to the center of mass, it's still 0. It's going to be 0 regardless of what I do here. Okay. And that will equal I, the moment of inertia. Okay. As such, from that, we're able to state that the moment of inertia is, where's my, from therefore, the moment of inertia I is equal to I with respect to the center of mass, which is going to be mr squared plus mh squared, which is what we set to prove. Now, that formula allows us to save work without having to do much integration. Instead, they can figure it out anywhere along the axis. I can figure out a moment of inertia anywhere along a particular axis without having to do all the integrations. That's what this parallel axis theorem allows us to do. So, okay. And you will have tonight in your homework exercises, you will get to work with this parallel axis theorem. You will get to work with it a bit more. Okay. Okay, we're kind of going a little bit backwards since I know we've already discussed it, but that's okay. I don't mind going backwards and explaining some things a little bit in more detail here with us. Okay. So, are there any questions? All right, when would you use this? Okay. For example, let's say I want to find of inertia of a sphere about the diameter, about the tangent line. About the tangent line. Okay. So, starting visually along this point, I already know the moment of inertia through the center. So, I is equal to the moment of inertia, which is 2 fifths mr squared plus 5/5 mr squared, which is 7 fifths mr squared. And that should make sense. Okay. This number here, 7 fifths, is bigger than the 2 fifths, right? Meaning what? There's more resistance to rotation about the end. And that could make sense when you're trying to spin a ball, correct? It's easier for you to spin it about the point of its center than it would be for you to spin it about the diameter at the edge or on the tangent line. Okay, so that's an example of when you could use this theorem. There will be plenty of other examples when we'll do that. Okay, but we got through what we needed to get through. Now, so I want to spend the rest of my time, because you guys have final exam next week, and so I do kind of want to finish a topic before we get that. Before we do start reviewing, we'll be reviewing Thursday and Friday, and of course your final exam, you will only see me on Wednesday of next week. So I do kind of want to finish a topic because I want to start thermodynamics at the beginning of next semester. So thermodynamics, which happens to be my least favorite portion in physics, but that's okay. So now, there's a point I want to get through your thick little heads before we continue. Okay. So please write down equilibrium and we'll talk about it. We have about half hour to go. Okay. Equilibrium, recall that when I speak of equilibrium, we mean, right, when the sum of external forces is 0. Or in mathematical notation, we say sum of forces externally is equal to 0, like this. Recall that even though mathematically the sum of external forces is exactly the same when it's 0, and it's the absence of external forces, right? There's a huge difference, correct? There's a technical but huge difference. The absence of external forces means we're following Newton's first law. The sum of external forces being 0 means something completely different, a situation which we call equilibrium, okay? Or dynamic equilibrium, another way of saying it, okay? When the sum of forces is 0, meaning that I can balance something with two different forces, F1, F2. And we've been talking a lot about rotation. Okay, we've been talking a lot about rotation lately, have we not, with torques, moment of inertia, angular accelerations. Okay. What if I have something like this that's hanging off the sign, such like this. Now I have two conditions to work with. In this top situation here, f1 plus f2 is 0. Now, like I have assigned, it can, with these chains, with these ropes, whatever they are, whatever you want to call them, it has a tension. Okay. And now I have two situations to figure out whether it will be rotating, like kind of swinging and kind of rotating itself, or whether the forces will stay 0. In the second situation, we have to have also the torques be 0. This is a situation which we define to be static equilibrium. So please write down this definition in your notes. Okay, so the definition of static equilibrium is when both the sum of torques and sum of forces are 0. Okay? Okay? Or in a mathematical notation, the vector sum of forces is equal to 0, external forces, by the way. And then the sum of torques, also 0. We're using Greek letter tau for that. Okay? Those both conditions, this is what we call static equilibrium. When both the torques and forces are 0, we have two conditions which must be true in order for us to work in static equilibrium. Fortunately for us, it's 0. So we can figure out anything we want, okay, with these two conditions. Okay. It's important. Both have to be 0. So you cannot do these problems. I'm going to make sure you take very good note of this point. That you cannot these problems with one set being 0. Both must be 0. Okay, so I know many people would just fall in the trap to start doing Newton's laws in these problems, would just start doing Newton's law for linear acceleration and ignore the rotation and end up getting the problem wrong because you forgot to take into account the sum of torques. Okay, so make sure that when you do such a point, that we have that both conditions are taken into account. Okay. Everybody ready for a simple example? Okay. It is also very important before I move on to discuss one point more that is very careful where you choose your axis of rotation. Be careful where you choose the axis of rotation, because sometimes that will make the problem 1,000 times harder. Okay. All right, here's our very simple example. This will be our only example in today's class, and your homework will be very simple from the textbook, nothing too complicated at all. Actually, it'll just be a worksheet that I have for you, and it's downloadable at the site. So it's clear. Okay. Let's see. So here's our example. We have a 3-meter long ladder leans up against a frictionless wall at an angle of 60 degrees with respect to the floor. What is the minimum value of the coefficient of friction that will prevent the ladder from slipping? Okay. So I'll write down the example. So what's this coefficient of friction such the ladder doesn't slip? Okay. So the first thing we need to do is, of course, draw pictures to set up our solution. So I would go ahead and erase the problem. If you need to go back, this lecture will be available for you probably within about half hour, maybe a couple of hours after, depending on how fast YouTube decides to load it up. Okay. So we need to draw the picture to prepare ourselves for the problem here. Well, actually, before that, we need to state what is given. We're given the length of the ladder is 3.0 meters. We're given angle theta is getting 60 degrees. And we want to find the sub s, or the coefficient of friction. Okay. So let's set up the problem. Okay. Recall what I said. that it is important to know we have two things to set up here in this problem. Okay. So here we go. Here's our wall. And there's our floor. I know, great art, right? So this is our ladder. This is angle theta. The ladder has a length of L. Okay. There's no friction against the wall at all. And so the friction is against the floor. So now we need to set up our forces. Okay. There is, okay, a force against, there's a normal force here, call that N1 for the sake of simplicity. I identified it first. Okay. I know there's the weight of the ladder from the center of the point, center of the object here. The ladder has a weight. We'll define that as mg. Okay. And then we know there's a normal force here, N2, and there's a force of friction pointing inward. Now, okay, and there's a force of friction here. Why is it going inward instead of outward? Right? Because the ladder will tend to slip towards the out. Since there's no friction on the top wall, it's going to slip going outward, so that friction will be going in. Okay. If friction was going the other way, if friction was on the wall, then it would be going the other way. Okay. Now, so from here, we have two situations to set up. Okay. So let's set it up. Okay. So we have our sum of forces in the x direction. Here we have 1, 2 forces here. Okay, we have to define a direction for acceleration. Okay. Okay. We have to define an acceleration direction, which we did not do in this problem. We can define it to be this way. Okay, and so since we defined it that way, we'll make that N1 minus the friction force is 0. Why? Because it's in static equilibrium. We don't want it to slip at all. So the idea is for it to not slip. How can we have it not slip unless everything is going to be 0? Fair enough. Next situation we have to set up here is some forces in, of course, the y direction. Now the y direction, we have a little bit of forces in the y direction here. In this situation, we have normal force in the second direction minus weight of the ladder is, of course, 0. Because it's, again, not trying, we're trying to make sure it doesn't move. Okay? So now we have a problem. Okay. Right, with a torque, we need a distance. Okay. So we have to define two distances here. We'll define this as d1 and d2 over here. Okay. Okay. And of course, torque is defined positively as going counterclockwise, but for the sake of the problem here, we have it defined the opposite way. Okay, actually we don't. Okay. Okay. So for our torque, as you know, the maximum torque is when it's perpendicular to the axis. When the force and the distance are perpendicular to that axis of rotation. So we're going to set up the sum of torque will be, in this situation, it will be, right, our axis, our point of axis is going to be the center here. So this is our axis of rotation. I defined it right here. So 1/2 distance here, so 1/2. So our d2. So before we do that, d2 goes from here to here. Okay. Now we have distance 2 multiplied by the weight of the weight of the ladder. Okay. That's one tension here. That's one torque. Okay. Going again counterclockwise is the positive direction here. But again, because I've defined acceleration to be going this way, this will stay positive. Okay. Now, from here, we subtract distance 1 from normal 1, and there is no torque about the center of rotation, about the axis of rotation. And because there is no torque at the axis of rotation, this is a very important point, this will all equal 0. Okay? Now, from here, d1 and d2 are not we made them up. So we have to take, so in order to get d1 and d2, we have to get it with respect to the lengths of the ladder. Okay? Genuinely. So d2 here is 1/2 length of the ladder times cosine of the angle here, theta. So it's going to be 1/2 length of the ladder times cosine of theta times mg minus d1, which is the total length of the ladder from here to here, times the sine of the angle there. So it's going to be full length times sine of theta times normal 1. Okay? Everybody with me? Everybody with me so far? And this all equals 0. From here, I can solve equation for the first normal. So I'm going to take this and solve it like this. And I'll state in 1 the sine of theta is equal to 1/2, or 1/2 L, sorry, that's not D. 1/2 L sine of theta is equal to 1/2 L cosine of angle theta times mg. Okay. Dividing, solving for normal 1. That kills that. Oops, sorry. That kills that. That kills that. That kills that. Cosine over sine is going to be cotangent of the angle. So I end up with n1 equals cotangent of theta equals 1/2 cotangent of theta times mg. Now, does anybody see where we're running into a problem here? Yes, we have the weight of the ladder. Okay. So now I can state that the coefficient of friction from this point, okay, I already know that the coefficient of friction will be normal times m2g. Okay. So now I already know. So I know from here, can I erase this, everybody? Yes, da? Okay, good. So I'll go ahead and erase this pretty picture. I know that normal 1 is equal to the coefficient of the friction force. I know that normal 2 is equal to m times g. Okay. Is equal to 1/2 cotangent of the angle theta multiplied by mass times gravity. Weight of the ladder, basically. Okay. So now I have a situation here like this. I know that the force of static friction is equal to the coefficient of friction multiplied by the normal force. In this case, the bottom force is normal 2. So that actually ends up happening to be the weight of the ladder. So that works out perfectly. So I end up with 1/2 cotangent of angle theta times mg is equal to mu times mg. That kills that. Mg kills mg. And we end up with mu is equal to 1/2 cotangent of angle theta. Easy enough. Mu is equal to 1/2 cotangent of the angle, which is 60 degrees. Okay. We bust out our fancy calculators. Okay. Right, so 1 divide by tangent of 60 degrees. 0.572 times 1/2, 0.29. And so we end up, after all this work, we're getting a coefficient of friction of 0.29, roughly, something like that. Okay, so what is it telling us, really? So it tells us, actually, the length of the ladder and the weight of the ladder don't matter at all. It is just the angle at which you're holding the ladder is being held against the wall, or against the floor in this case. Okay, that will dictate whether it will slip or whether it will not. Okay, so what that expression shows us is that when the angle increases, what happens? What do you think happens if I were to increase the angle? What would happen to the coefficient of friction? Would it increase or decrease? Well, why don't we try it? Okay, okay. A little bit confused. Why don't we try it? Okay, why don't we take 1 over tangent of, say, 80 degrees, something like that, times 1/2. Right, it will decrease. The coefficient of static friction is going to decrease. Right, they're inversely proportionate because it's probably better represented. You probably don't tell it from that. It's 1 over twice tangent of angle theta, like this. Okay. So as my angle increases, the coefficient of friction will decrease. So it's important to note that the angle at which you hang holding the ladder is the most important thing in determining whether it's going to slip or whether it's not going to slip. Okay. And obviously, the less friction that you have, the easier it's going to slip. The easier it will be for it to slip. Okay. All right. Homework problems will be downloadable later from the site. Okay. You guys know where to go on that by now. So until then, I will see you tomorrow, and good luck. All right.